Hello, everybody. It's been a minute, but I'd like to welcome you back to another episode of Anomalous Experiences with your host, Brendan McNamara. Today, I want to reintroduce you to a wonderful individual who has taken it upon himself to understand or attempt to understand a great many of the mysteries we face around the UFO and UAP subject, specifically where it comes to propulsion, and has put a great deal of effort into understanding and explicating the mysteries of general relativity and quantum physics, where it applies to warp drive and fast and light travel. We've done a session with Daniel Davis before, but we had still some questions hanging out and some things to clear up, and I'm glad that he took his time with me and us to explain a few more things about the mysteries of the universe. And so, without further ado, I'll turn it over to him. Enjoy. Thank you.
All right. Hey, Dan. So we were just chatting before I hit record. And by the way, hi, everybody. This is Anomalous Experiences with Brendan. And today it's Daniel Davis. And we were talking general relativity, quantum physics, and warp drives and other such mayhem. Last time, well, you take it from here. What were we talking about last time?
All right, so like last time we just kind of like went over really briefly on like what general relativity is, and I guess we'll kind of go through and do it again.
Okay.
So basically, simply, so you have your G mu nu equals 8 pi G divided by C to the fourth equals T mu nu. Okay, it's literally Greek to me, right? So this is your stress energy tensor and your space-time metric. So the Einstein tensor. What this is saying is, so this is your space-time curvature. This is how much energy is in the space-time. And in the terminology that was coined by John Archibald Wheeler, space-time curvature tells mass and energy how to move, and then mass and energy distributions tell space-time how to curve. Okay? So let's get rid of this for right now, because we don't see it. So what is this G mu? Okay, so we were saying that this is broken down into a series of a bunch of equations. Okay. So, and remember what I was saying about, and I didn't go too much into detail on it last time, but we'll go a little bit more this time. So you have like G00, G01, G02, G03, G10, 2030, 11, 213, 2122.
So these are space-time curvatures of different objects.
Yeah, so
or different space-time windows, or what are we looking at here? Just put in context.
So we're going to get rid of these bottom ones here because they're always inverse mirrored of the ones up here. Okay, so we'll get rid of these ones. Just be right back. The dogs are barking to come in. Okay, so
Gotcha.
What's going on here? So these ones down here, these are your dimensions through time and X, Y, and Z. And then these ones up here are the protractors, the angles between those dimensions. So I'm sure you've heard about trying to add up to make sure your triangles add up to 180 degrees. That's this part up here, so the degrees. And so if you count these, you have your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are your 10 partial differential equations that people talk about when they're saying they're solving for Einstein's equations. So let's get rid of the protractors because we're not that worried about them today. We're just going to worry about distances, basically. So what are each of these? So we're going to remap these out, the G00, G11, G22. And so remember, these are the T, X, Y, and Z dimensions. So let's rewrite these out in a little bit more, less convoluted form. So we're going to say our G mu nu is equal to our ds squared. Okay. So just kind of get rid of this over here. Now that we know that G mu nu is roughly on the order of ds squared, so we can say that ds squared is equal to, and now when you have something called the metric signature. You can choose either one. It doesn't matter because they're equivalent of each other. You can either do negative, positive, 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 or you can do positive, negative, negative, negative. Doesn't matter. It's just you just have to pick one for whatever reason. So we're gonna do positive, negative, negative, negative right now. So dt squared minus dx squared minus dy squared minus dz squared. Okay, so you notice each one of these are squared. Well, where is the square term coming from? Well, remember, so this is our G mu nu. This one is going to be our G00. So we can say that the G00 is equivalent to GTT. So that's why it's T squared, because you have two T's here. And then this is your G11, G22, and G33. So GXX, GYY, and GZZ. Just so you can kind of see what's equivalent. Camera can't see you. It's okay. So that's basically what's going on here. So what kind of people mean when they say they're finding the geodesic or something, the straight time, the what would be your straight path through a curved space time.
One geodesic being like the path of light, for example.
Yep.
Okay.
And so let's just go to like a really simple example. Let's get rid of all this here. So we're gonna say our ds.
I'm gonna walk away. I'm still listening. I'm walking away from the camera so I can find a pencil. I'm trying to take.
Okay, no worries. We're just gonna say our ds is equal to the difference in time minus the difference in the x and let's just say the y dimension. So dx, so ds is equal to dt minus dx dy. So what does this mean? So let's say if we have a point A.
And that little tilde symbol, that little approximate symbol, it kind of means like on the order of, or
yeah. I use it instead of the even though
it's good. But it's not exact, but it's on the order of. You can leave it that way. I was just explaining for the audience.
It's okay. I normally use on the order because I do mapping calculations.
Kurtjai Mungol does that. Explain why he does that. Yeah.
So let's just say that. So here's our distance over x. So distance over x. We add up the distance. So our distance over time minus our distance over x minus our distance over y will give us our distance from our point A to point B. Okay, and so we're basically just taking this and we're expanding it out for all of space time instead of just a regular x and y map.
Gotcha.
Yeah. So that's kind of what's going on there.
And that's what you mean by all the angles add up to 180, as if you were seeing like the entirety of a space-time window or a space-time curvature or one of these geodesics, like all these, like it's like, okay, sorry, probably butchering this, but it's this triangle that's a right angled triangle that is the same as like one of these XY coordinate plates.
Yeah. So if we're
with a
doing
line
like from
going
our
through it.
local frame of reference, let's think of like
And it looks like a
Like a-
straight line, but it's actually a straight line up through a curved plane. Yeah. Or
basically, yeah.
okay. I'm just trying to conceptualize it because like a lot of this GR stuff is, well, it's literally rocket science. But or rather UFO science. So yeah, I'm trying
Rocket
to.
science is Newtonian.
Okay, gotcha. Well, we're getting there. We're getting to a new paradigm with this. Yeah.
So let's now that we kind of got that, like a basic lesson on like what general relativity is in your head, let's go over what the Alcubierre metric says, and like a very basic implicit form, just basing off of our four dimensions that we're working with here. We're not going to worry about the protractors right now. We're just going to worry about the dimensions.
Okay.
So for the Alcubierre metric, we're going to say it's ds squared equals dt, and my marker is getting blank, so I'm going to switch to this one. Oh, yeah, that's better. dt squared minus dx. So this is going to be for a warp bubble moving in the x-axis only.
So those subs, those are d sub s squared, d sub t squared, or
Just dt. It's not sub.
Okay.
So a sub would
so
be
the
down
distance is okay. Okay, so it's dt. Does that mean they're timesed, multiplied by each other, or just you're identical? Okay.
So minus v f r dt minus dy square minus dz square. What? Yeah, that's why I said because it's the only way that it gets the computer off, because otherwise the light will. Sorry, my
No worries.
daughter woke up. She's asking you about my setup. It's you don't want to know.
Yeah, it's all good. One sec. Do I need to pause the recording or
Oops, sorry.
No, we can edit it. You're good.
life
She's
is life be
fucking
life?
off.
I got it.
Yes, we're recording, babe.
See a laptop sitting on top of a lamp. It's 2 a.m. I'm going to sleep.
Love you too.
What a tolerant wife. I mean, fiance. Just tell her what an amazing partner she is, putting up with your ass.
Ain't no drama when you got marijuana.
That's the truth. Unless your partner doesn't smoke, which mine never did. So, what can I say?
So again, this is our geode. So this is like we can say this is the path that the warp drive is taking in this particular context. So we're saying, that it's distance over time basically is, and then we figure out and so again here we're only moving in the z-axis. We're not worrying about the other dimensions. So v is our velocity, and then f is our shaping function, and the parentheses of r tells us that our shape has a radius, so we can infer that it's a spherical warp drive in this case.
Okay, hold on. So d is your velocity. D is velocity. I'm trying to make my key here. D is velocity. F is warping function.
So you notice I'm basically we're just expanding the parameters around the x dimension here.
Okay.
So it is right back our original form before, ds squared equals dt minus dx minus dy minus dz squared.
Yeah. Okay.
So if you notice here, this all stays the same. This stays the same. And because we're only moving in the x-axis here, this is the one that gets expanded with the parentheses. And so then we're introducing another dx term or another dt term over here. So this tells us our distance over time in the x-axis along a certain velocity, the v over here, and then this tells us the shape of our bubble. Is that making sense?
It's coming together a little bit more from the protractors earlier, that only involve three dimensions: time, distance on the x and y axis. Now we're involving 4 dimensions: time, x, y, and z. And this function, when you plug in a certain radius and velocity into this function, it's going to result in a certain amount of velocity on the x-axis, which would be, given direction in space, is what I'm picking at, sort of.
In a given direction of space over time. That's why we have the other dt parameter over here,
Right.
in the overall. But yeah,
Your speed, how fast you're going.
and that's the
And
velocity here.
even though you're not technically moving, this is how fast you're going to the
velocity of the bubble.
observer. Yeah, the outside observer, this is how fast the bubble is traveling
Yep.
through space as a result of these parameters that you're plugging in. That basic concept I get, and the rest I'm putting together as we go. So that we're okay. So the dt, dx squared, dy squared. So that whole just giant chunk is replacing the dx squared.
Yeah, so this giant chunk here is replacing this here. And you can still, find this. And, I'm supposed to have a squared function. Oh, well, I fucked up.
Nope.
Yay!
Yeah, we better iron that out before you go on.
Yeah, no, I've
8-pack caught
still caught myself.
It's all good. It's all good. You did. And I'm sure the others have made worse. So you're doing it. You're doing the thing.
And I mean, like, we could write this out in more detail too, and we could start to make modifications to it and talk about some of the modifications that people have made.
And I can start to see where different factors can be plugged into this. Like where my brain first goes is obviously this is a Cuvier, so that requires like ungodly amounts of energy. Where in here can we reduce the energy requirement? And
all right, so
reducing the size, the radius, maybe, and all that.
So there's a few different ways we can talk about this.
Right.
So like, obviously, you're a Cuvier. So let's say here's our work drive. Here's our little tic tac. All right, let's go to tic tac.
Okay, let's build a tic tac today.
So classically, for an Alcubierre drive, you have a gravity well here, and then flat space time, then expanded space time here.
Right.
Okay. Now, normally this either takes a lot of energy and negative energy. What happens, and what people have been trying to do rather successfully, might I add, via various different techniques, meaning there's
several.
More than one.
Yes, we have now going on 20 different, really pretty practical warp interpretations.
So it seems like this works too. So we have positive on both sides.
Okay, hold on. I'm going to draw another version of that. So that somehow reproduces the effect that we're looking for.
This just makes the bubble
a ton of negative energy in front. Okay.
But this doesn't. So this is just a bubble. But now this bubble doesn't move.
Now, okay, one sec. Which bubble doesn't move?
This one now. So see how the positive gravity wells on both sides are even.
Right. So the bubble inside doesn't move, just space moves.
Yeah,
which is how allegedly a warp drive is supposed to work.
All right. So if I'll go back, let's go back to our Cuvier metric.
Okay.
When it expands here, this is causing a movement in this direction. Okay. With our all positive one. When they're symmetric, there's no motion going on here, so it would be stationary to its frame of reference.
These are equal wells, equal wells.
So if we want to move, and this is what a part of what Heisenberg's paper, Lavinia Heisenberg, not Werner, he or she talks about, you take the same amount of energy overall in the bubble, but you make it asymmetric. So you put it, have more heavy on one side than the other. Then that's what will give you your motion.
Okay, so heavier positive energy behind and
So
lighter
a symmetrical
positive
warp
energy.
bubble is stationary, and an asymmetrical one gives movement.
Okay. So this is greater than this. Okay. And that allows you movement. So is there anything to the symmetrical one? Is that a paper that somebody came out with before Lavinia?
So like a spherical one would be
spherical work. That's like
so like a
Shoshani.
positive energy spherical one. The Lavinia paper, she plays around with a few different geometries. I'd have a couple on my computer. I'd have to link them to you, but I can do that after.
Okay. But Lavinia's interpretation, the other Heisenberg interpretation is the asymmetry allows for a similar effect as the difference between the negative and positive in Cuvier's original.
I believe Chance Glenn talks a bit about this. I know Greg Hodgin does a bit too, though he's not publishing. He's running a business trying to get funding for this, I think.
Now the question here in the spherical interpretation where the wells are symmetric, where they're equal, is that, I mean, you said it doesn't move. Does that just simply mean that the object is not moving through space, but there's a different format for that movement? Are we moving time? Are we moving space? So
it would be like staying local to its local reference frame. I mean, like
okay.
I guess if you made it strong enough, you could get it to separate. But
okay,
you don't know.
So that's like, in a way, if we were building one of these things and you just wanted to warp out and stay stationary, like remove yourself from the space time, that'd be a way to do it. Like warp a city, and like just cloak a city by, putting it inside a warp bubble. Kind of like some of these.
Just guess technically.
There's some descriptions, some interesting descriptions of locations from like the Mahabharata, for example. I don't want to get into details, but it sounds pretty close to like Indralok, the location of Indralok. Very much sounds like you're going into a warped city.
I'm starting to get into like Vimanas and stuff.
Well, that's the flying craft, which also sound interesting. But you go into this location and they describe going through several gradations of time movement and rainbow shifting, where the spectrum changes and the light changes, and then all of a sudden you thought you were going into like a rock or something like that, and all of a sudden you're in this giant city that you didn't see.
So like what some papers have shown is like when the bubble itself is moving faster than light through space-time, the vacuum starts to kind of act like a fluid around it.
Okay.
And so the paper called Warp Drive Aerodynamics. I'm drawing a blank on the author's name right now. He finds out that you can really reduce the energy requirement. So let's just say we're starting with a spherical bubble, right? And you have all this energy that as you're going, as the bubble's going, say this way, for example, you're gonna have all this blue, this energy, different virtual particles from the vacuum itself. They're gonna start building up on here as they get blue shifted, right?
Right.
And that can destabilize the bubble over time. There's things you're gonna have to start doing to deal with this, and you'll notice that more and more of them are, quite a bit of them are this is basically the reason why balls, spheres aren't that aerodynamic, and an atmosphere is a similar amount.
Yeah.
Similar.
And so that you have an accumulation of blue shifted particles and radiation on the forward side of this thing moving forward.
And so then they go to a more aerodynamic shape. And I'm just gonna use a TikTok again here right now, just for the comedy of it, I guess.
Right.
But you can obviously get more and more aerodynamic shapes than. Right. This is more aerodynamic than a sphere. And so what they
I think
find
that
out,
Tic Tac is just made by people that are like, fuck it, we're gonna make it any shape we want, just to prove we can. Like, let's make it
look
a
what I 3D
toaster.
printed.
Oh, dude, bro, I have to get that done. I have one of those too, and I'm not a Tic Tac 3D printed, but I 3D printed my
I got a
own.
sport model here too.
Nice. I 3D printed the DeLorean from Back to the Future. My next
Nice.
move I'll have to 3D print one of these UFO models.
So what they find out about the more aerodynamic model here is what happens with the radiation is it still builds up a little bit here at the very front, but for the most part, a lot of it ends up getting deflected around it, and something kind of similar to laminar flow around a wing.
Mhm.
And so basically the finding from this paper is they can use this principle to really reduce the energy requirements a lot more if you start to going more and more aerodynamic designs than you would a sphere. The sphere just makes calculations simple. Is why most people use a sphere.
So the physical shape of the craft does actually make a difference.
Yes.
In how it performs, regardless of whether you're creating a warp bubble. There's no free lunch here in aerodynamics land, even so, because space starts to get a density once you are moving fast enough. Yes.
Basically, yeah.
That's
a good way of looking at it.
It's not a vacuum. It's polarized medium. So it's another kind of fluid. Once you move very quickly.
So if we want to look at what one of these equations looks like in its modified form instead of its regular form.
So when they say like Alcubierre, they were saying for a while, the warp drive concept doesn't work because you'd be piling up so much radiation on the way over that when you stop, that all that blue shifted radiation would suddenly depart from the surface of the bubble and radiate and destroy the world that you were trying to visit. That would not happen.
No, that would still happen.
That would not happen as much.
It just wouldn't happen as much. You still do get these points of blue shifted. They just might not be infinitely blue shifted.
Right.
Now you're still going to get this energy dump when you come out of FTL speeds. Now this is not a physical barrier that stops the warp drive from existing. This is an engineering problem to some degree and a safety degree in some problem. I guess a good analogy for this is
that's what I was telling these hecklers on the Facebook.
Well, when
they were heckling me about
when you drive a car. Do you drive the car through your front wall?
Right.
Or do you stop in the driveway and get out?
When cars were being invented, though, there was some heckler saying, if you invent this thing, it's just got to keep going through the building. You're like, yeah, but we can deal with that. We have this idea called brakes.
Yeah. So if we just want to make a model of that, so let's say here's our planet, right? We come out of space here and we're facing this direction. We're going to dump bunch of X-rays at our planet, and that's not good. But what we can do is if we come out of FTL on a tangent here from the planet,
right,
and then curve around and finish, turn 90 degrees and finish the rest of the trips slower than light, it's no longer an issue.
Yeah, that and reducing the the forward the size of your fore shape, like your bow, basically, making your bow more spatiodynamic, so that it resists that less, and just coming out at like a tangent. Yeah. Okay.
So this might be a signature we could look for potentially. In terms of how we might be able to pick up signatures from some of these things. Now how specifically that signature would manifest, I guess that would depend on the particular dynamics of that specific warp drive. But so if we're gonna look at one of these modified Alcubierre metrics, which isn't Alcubierre anymore. So again, we're gonna start with our ds squared. And this one's going to be a little bit bigger, so I might have to make it a little smaller. So dt squared minus So V, and then we're going to put F up here. X, Y, Z. Oh, getting ahead of myself. Minus K, T.
Why doesn't the Z have a sub one there? There.
Oh, those are commas.
Oh, comma. Okay.
My bad.
No worries.
Divided by
Matters. I've never seen the equation
A,
before.
X,
X, Y, Z
Z.
minus K, T. Okay.
Squared.
Over.
God, I'm really getting ahead of myself. So, yeah, I can fix it.
Okay, do it. You're good. You're good.
dx minus v. Yes, fixed it.
You fixed it, but I'm using
Minus
pen over here. So
y square minus dz square.
okay. Putting that out. So that's a D out front or an alpha?
This?
Yeah.
A alpha.
A.
Yep.
Okay. I just draw an alpha, yo. A gets confused.
So this specific modification is from Gianluca Persiano, professor from Italy, who's been working on this quite a while. And this really so A, what this does is it reduces the energy amount to a seemingly arbitrary value for needing to make a warp drive. And while this specific one doesn't get rid of the negative energy requirements, it does lower it to a level where the Casimir effect becomes viable to use. So there's two different approaches that we have right now for the negative energy problem. One is lowering it enough to where you can use the Casimir force, and then the other one is just getting rid of it altogether. Both seem relatively valid.
Okay. 1 second. Hold on. Oh, you guys, is everybody happy? Something dropped off? Okay. Kiddos back from La La Land. All good? Okay, cool. Sweet. You're gonna go over that last little tiny little bit, the last 5 seconds of your download. Oops. Yeah, hold on.
What?
Resume. All right. Where were we?
So this particular metric, like I was saying, this comes from Gianluca Persiano in Italy.
Jean-Luc. What was that last name?
Persiano.
Persiano.
So do you want me to write the canonical Alcubierre metric above it so we can compare, or do you have it there in your notes?
I might be able to pull it from memory. Let's see. ds squared equals dt squared minus the bit in brackets probably gonna have to go look back up. But dy squared. Well, the bit in brackets is the important part, right? So let's look. Okay. Yeah, you might want to just do it. Yeah, do it up there again for the folks back home. Dx minus velocity function of radius, distance, time. Yes? Squared. Yep. Okay. Just calling out the factors as I see them. All right, so Jean-Luc Persiano, and then we have Alcubierre. I'd love to know where our friends Dr. Sarfati and Dr. Pais fit into all of this. So I can interpretation standard. Those are variations on Persiano, because Sarfati was saying things like, you could run this on a 3-volt battery and this and that.
Yeah, so I can get into that a little bit.
Right.
So first let's
we're finding our location in the field. No pun intended.
So we can see here that Persiano, he's introducing a more complex shaping function. So he replaced, so the shaping function f is still up here, but instead of it's no longer a radius, we now have coordinates
instead of one. Here. Yeah, one blind radius. It's a very looks like this is a very unique shape that he's creating for a warp bubble of different geometric properties that might do better than just
Yeah, and so this one's
simple sphere.
dynamical.
Okay.
Yep.
That could be a tic tac shape or a donut shape or a toaster shape or heart shape. If a heart shape ended up being like super good at this for some reason. Okay, on the outside of that
And again, these are ones for just moving in the X direction.
I forgot to put the DT up here. DT.
Oh, this one?
Yeah, but forgot the DT. No, and in the new one, DT outside this big bubble that's got all this stuff. The F over F this minus KT over alpha this minus KT. Okay. And then there's the DT.
Does that help?
I got it. Yeah. It does help. That was hard to see. But I got it in there now. Cool. That's important. I don't want to blow up any planets misdesigning my warp drive.
Yeah, right.
Yeah, perfect.
Balance this back on my lamp.
Man, we need to get you a proper like laptop stand boom thing, and
just like an actual decent camera.
It's not that much. One of these little Logitechs, you can get one of these little squiddy tripods, and get one of the little Logitechs.
Gotta get one that like comes out and drops off the ceiling or something.
You can. Anyway, we can continue.
Yeah. So again, these are just for again, these are both written for a bubble that's moving in the X direction or in the X axis over time. And if we're going to start, moving in both the X or the Y or the X or the Z or X, Y, that obviously the equation is going to expand out and get bigger from there. This is just making it, easy, shorter and easier to read for my limited amount of space that I have here, and making it big enough for the camera to see.
Right.
I want to go over one other little thing first, and then we can get into what we were saying or what you were asking about with Patty.
Yeah.
Actually, I'll just answer that question first because it's a pretty easy one, and then I can lead that into where I was going next. Anyways.
Okay.
So, you were there for the APEC conference where I was asking that question about changing the speed of light.
Right.
Okay, so the analogy that I used just to as a dumb down, if we're dumbing down from general relativity to special relativity, I asked is he making C a variable to adjust the lengths of your spatial and temporal velocity dimensions, and he says roughly speaking yes. Now what he's actually doing, and again, so let's look at Einstein's. So again, G mu nu equals 8 pi G divided by C to the fourth T mu nu.
So hold on, your G mu nu. So I got a mu, and what's nu? I'm not.
It's just like a V, basically.
It's a V, okay, but it looks like different than a normal V, I'm guessing.
Squiggly V.
Okay. I like the symbols.
Greek to me.
It is Greek, but I like algebra. I want to respect it. So over 8, and so that equals 8 pi. That's a pi, right?
Yep, 8 pi big G divided by C to the fourth.
Over C to the fourth. Is that a little c to the fourth, as in speed of light?
Yeah. Yep.
Okay. C to the fourth. What up?
I'm just getting Legos.
Really?
I wanted to get Legos because
They're not in here. They're out there.
Then where are they?
They're in the big tub out there under the awning.
Hey, Key, do you want to come inside and play with Legos?
No, he's good. We're good.
Okay,
It's all good. Just be heading to bed anyway.
Yeah. So at midnight there?
Yeah. Yeah, revealing my parenting frivolities. Well, what's up? I'm pausing now.
Okay.
That's going to be a lot. All right. So the big T sub mu nu.
That's just your so your spatial curvature is proportional to your, proportionality constant to your energy, and you can run that both ways.
Okay.
And so what? Again, so kind of building off of our special relativity analogy, if you change, because to keep this whole thing consistent, if you change something in the constant, it'll change the either the your curvature or your energy. If you're changing one of these changing your proportionality constant. So what Spatty is talking about doing. So he's taking C, and so what is C equal to in electromagnetism? C is equal to 1 divided by the square root of
C equals, let's see, small
is
c.
so it's the so C is equal to 1 divided by the square root of the the electric permeativity and the magnetic permeability. I might have had this backwards, but
electromagnetic
the permeativity and permeability of the electromagnetic fields.
I'm going to have to get a rerun on what the difference is between permeativity and permeability. They sound.
This is just what Sarfati is proposing to do. Proposing to do, and he's saying that you can do this in metamaterials. He doesn't specify what those metamaterials are or how.
Is that an epsilon under the square root? So epsilon
and mu.
Son, what's under? What are the subs? Are those not subs?
0?
Okay.
Yeah, 0 and 0.
Okay. I'll do it again. I want to know. Oh, okay. So you can put that in there. And after epsilon was a mu. And that stands for.
Yeah, and I might have had those backwards. I have to go back and look at his paper again. It's 3 a.m. here. I'm sorry if I got that wrong. Flame me in the comments.
Yeah, it's okay if you got it wrong. I just want to I want to transcribe this accurately, as accurately as I can.
I can go
and if you got them wrong, we can look that back up, and then I can go change my notes.
Here, let's.
I don't want to make a bomb. I want to make a UFO.
Patty's paper right here. I can just look it up, I guess.
So you can go, the basic thing being, you can go and plug in for C this.
Yeah, epsilon and mu.
Yeah. Okay.
Or another way that we could write it instead of the square root, we could write it as C squared is 1 divided by epsilon mu. Yeah, so we just do the square root of 1 divided by square root of epsilon. And so that's all that Sarfati's basically doing. He's saying if you use metamaterials to basically adjust this in the equation, you can drive the energy levels down. Okay. And so building off that and what we were saying about our special relativity context, let's talk a little bit more about energy requirements in the warp jet. So
C squared equals 1 over the square root of epsilon and
C equals 1 over the square root of epsilon 0 mu 0, right. Or C square equals
all that squared,
or C square equals 1 divided by epsilon mu.
Okay, got it. So C squared equals 1 over epsilon mu. Okay.
So if we're going to look at
not mu naught. Okay. So then if we were going to plug that in there, all that gets squared again because it's C the fourth over here. Yeah. So that would be under the 8 pi g, you've got 1 over epsilon not squared mu not squared. Yeah, something like that.
Yeah, something like that. Again, I'm not too much of an expert on Sarfati's approach. That's just It's kind of generally what he's doing. If you go and read
And
his
some
paper,
people would be like, "No, you can't mess with C. That's sacrosanct." But in this, he's trading it
well,
around.
C is still staying the same overall, in that he's adjusting the ratios that make up that C. It's
okay, which is totally fine.
Controversial for a
in
reason.
Algebra. It's we're just doing algebra. We're not changing it, guys. We're just getting some new places. I think that's the essence of string theory, isn't it? Like,
I think that's it's not my
impossible
approach.
math.
That's Arcadi's.
It's so good. I don't need to go there, but
so let's just keep thinking about in this more simplistic special relativity case. For
okay.
So if we're going to pull some of the equations out of Yuri Yaroshenko's paper, escape from a black hole with a spherical warp drive, I've referenced this one before. So we're going to say that the energy of our warp drive is on the order of V squared R squared S C squared and G. Okay, so what does this? So what does this say? This is the energy of our warp bubble, and again, this is assuming a spherical one. Is
because it's got an R there.
Yep.
Okay.
So the velocity squared times the radius squared divided by the thickness. So epsilon here is our thickness now in this particular
What's the
equation.
sub on epsilon?
Oh, so it's just they don't need to be there. It's just denoting that it's of the bubble. So we could get rid of them if we want to, if they're confusing you.
Okay.
So
well, if they're the same for the top and bottom, that's all I need to know.
So for velocity squared times the radius squared divided by thickness of the bubble, and then times the speed of light squared divided by g. Okay. Funny enough, if I'll get to that in a second. So what we're going to notice about this particular one, let's take a look at our velocity. Notice it's simple, meaning this is for a constant velocity. So if we're going to put this out, if we're going to look at what this is sort of representing, and again, there might be some physicists that are going to flame me because this isn't a perfect one-to-one, but it'll get the point across. Right. So let's go to our space-time, our simple space-time diagram over here, right? Sanity odds of black hole. Blue is going to be our null geodesic, so the 45-degree lines that light follows upon. So these represent our speed of light.
Right. I was going to say, so a velocity sounds simple, but a velocity that's not simple would be like your velocity along a timeline curve, or something like one of these geodesics, which appears to be straight, but it's actually a long curve. Right.
So because these blue lines are 45, these are our 45-degree lines. Okay. These represent anything going at the speed of light. Okay. And so anything if something's, going along this path, so to speak, that would be, roughly 50% the speed of light, but still slower than light. What's this? Now,
they're pretty fast.
If we want to go faster than light and to, escape, get outside of our light cone, otherwise it's, the equivalent of escaping a black hole, basically, we have to follow a line that's more, or, that falls, on the outside of this 45-degree angle and into this area over here.
Right.
Now, if we're referencing back to our equation,
so that would be over here would be like 0.5 C, and over here would be like 1.5 C, right?
Yeah, you can go with that if that's what helps. This isn't a one-to-one exact.
Not exactly,
scale,
but
that's it's not to scale. It's
in my mind, like
qualitative approach.
So in terms of our coefficients of C, roughly those could be in the range. Okay.
So this being a straight line means that it's for a constant velocity. meaning it's instantaneously going that fast, and it is only going that fast. It's a bit of a problem, right?
It sounds like the flight parameters of some of our friends upstairs.
Well, no, because that's not. They're not. That's not.
They're not instantly.
It's not
accelerating.
instantaneous. It's just apparent, because they can
It
still
seems
measure
that
these on the
way.
radar.
Right.
5,000 Gs.
Yeah.
It's really hard acceleration, but it's not instantaneous.
There is
so
an acceleration.
So at 5,000 Gs, if the Tic Tac, which they measured at 5,000 Gs on the radar, if it could hold that constantly through time, it would only take an hour and a half to reach the speed of light. Even if it's like we were saying, even if it's really, really, even if it's really, really hard acceleration, it's not instantaneous. That's kind of partially what separates warp drives from wormholes. Is even though I kind of consider them to be two sides of the same coin, wormholes are instantaneous travel, whereas a warp drive, there's going to be some time delay between A and B. So personally, I consider my warp drives to be a non-instantaneous version of wormholes, and we can kind of get into that later. Or that could be a whole other video.
So, point being, a not instantaneous would be a curve, not a straight line, where it comes to your velocity arrow.
Yes.
Right.
So again, going off of like 45-degree line here on our space-time diagram. We can draw. So we start going slower than light, and then we accelerate, it'll curve, and then we pass that 45-degree angle, and we keep accelerating, and then we decelerate back again, and then we land up in this point here, and you'll notice this looks like a wave.
That's where I think I got the last time. I remember these shapes you were drawing last time we talked, and we sort of got right into multiversal travel going between the windows. And
well, this is kind of where we're going.
That's how it goes. Okay, so you start out slower. That's the part I didn't get. Is how is this reflected in speed? Okay, so this is lower than speed of light. It's moving into faster than speed of light until you go
away.
even so far. Blah. 1 second. 1 second.
So while with this model, you can't go directly back in time, but what you could do is you could take a two-step journey. So you do your acceleration, deceleration faster than light to go back, and then you end up over here.
Mhm.
And then if you run it again, and then you can end up over here. And then, that's how you would get back, farther back in time on your own timeline. You have to do more than one jump.
Or to a different location in space at the same time as you left, presumably in your own timeline in your universe.
Yeah, you could probably calculate for anywhere in multiverse, which is kind of what we're
which includes 5 seconds ago,
and so
at like Proxima B or something.
Yeah, you could tune it for hypothetically speaking, you could tune it for however you want for different things.
So each one of these quadrants on your set of axes here could represent a different space-time window or universe, or would you say Hilbert space?
Yeah, so like when we make the travel, we make the jump, our frame of reference is always gonna come with it, because observers are always at the center of their own universes.
Yeah.
So when we move over here, then this kind of goes away, and then it gets transferred over here to where we're sitting now. And then you could kind of, and again, this is only considering a very simplified version of one block universe.
Wherever you go, there you are. That's as my mom used to say.
Yeah.
Which is a big thing. Like I think a lot of people could stand to understand.
So don't this is an unfinished equation. So we're starting to get into my speculations. If we want to make our simple energy equation kind of reflect that more complex time curve, we could sort of modify it. And don't hold. This could be wrong because this is total spectrally. So
That's
we'll
a
say,
simple equation that has the radius, just a simple radius. Yeah.
yeah. So remember the one. So the E equals V squared times R squared times so the velocity times the radius divided by the thickness times C and G. That was our simple one, right? So if we're wanting to modify it, we could say it's our V square over T. No, T squared. For gamma for our relative for
So
our
that was
relative.
after the T in parentheses. Is that a little n or is that a mu or
So
sorry?
gamma for our special relativity, V then T in parentheses squared R squared divided by epsilon, and this is C squared G squared. You know, it's a modified version of our last equation. And again, this could be wrong, but what I think this is saying is that the energy at, again, we'll draw out our curve again. The energy at any point in time is equal to, the velocity squared at that given point in time. And then the gamma is here for our relativistic transition for,
Okay.
for
Your little squiggle looked like an N to me for a second. I forgot I was thinking
Oh,
squiggle. That was the problem. Like there was no N. Okay, so that's gamma velocity times squared radius squared over epsilon times C squared over big G.
and again, this could be wrong, so don't hold me to this equation. This is just kind of showing you like what it might look like if you modify it to account for the more complex where it's no longer a constant velocity.
Right.
So it's, the
Just
energy
like the behavior of a physical, like the behavior of a real object moving through space. It accelerates and decelerates.
Mm-hmm. Okay, so now how the hell does this relate to multiverse? Because we haven't really talked about that much yet. It's so it's the only way that can solve time travel paradoxes while still allowing for free will.
Okay.
So you could either say that just time travel just can't, you have the Hawking conjecture that just something will happen where time travel doesn't exist. The general relativity says that closed causal curves can happen, but that brings into questions like the grandfather paradox. Or the Novikov conjecture will say that you can go back in time, you just can't change anything. So there's your free will aspect. Or we could do it in a many worlds context.
Mm-hmm.
And that ends up fitting really nicely. So, and this is, I'm going to draw out a hyperbolic space here, and some people, that might make some people mad because that's more representative of an anti-de Sitter space than a de Sitter space.
I remember that,
But
that question you had of him. He's like,
this is valid in both.
Yeah.
So this is valid in both. So screw you guys. Flame me in the comments. I don't care. I can leak you papers.
It's a stopgap measure. It's where we're playing with concepts so that we can get a better understanding of what these initial concepts mean, even if that means playing around in alternative spaces. All right.
Well, so this space from entanglement thing, it's valid in de Sitter space and in Minkowski space and anti-de Sitter space. Right. I'm just drawing a hyperbolic thing right now because it's the easiest thing for me to draw to get the point across.
Okay.
And then we'll kind of make these each smaller.
This is also kind of adjacent to the anti-de Sitter space is sort of adjacent to the woodcut of the angels and the fishes, or it was the birds going countering with the fishes.
Yep.
Okay.
Yeah, so you're already picking up on the right on what you're supposed to.
It's a fractal basically of reflective parts where the smaller pieces represent like half moon.
Yeah, I drew that pretty good for how quick I did it. Huh?
Okay.
So now I'm just gonna erase this.
No,
guy.
I remember that you were dropping this diagram a bunch of times in the chat. Now it all kind of
it's
comes
useful
together.
for a lot of analogies.
And it's also that holographic video that you put up a lot that that's basically the guys moving through a 2D
Yeah,
space,
that's to kind of give you a look at like what it would look like
the
going
3D
through
guy
it.
is moving through a 2D space on the computer, which is represented in his headset as its own 3D visualization. Yeah,
and as he's moving through it, it's really wrapping around him when he's staying in the center.
Right, right, and that's the frame of reference is always your frame of reference.
Yep,
is always your frame of reference. Be here now, be here now, be here now. Yeah. Okay.
So we're gonna introduce this red guy right here, and I didn't have to yet because this could be valid for the whole circle, right? And then I'm gonna do a dotted line out here. So, and I'll let you catch up.
Yeah. The kids screaming at their Roblox games in the meantime. The kid next to me, is playing Poppy's Project Playtime. It's like the multiplayer version of Poppy's Playtime. If you can picture that, it's like all the terror of Poppy's Playtime plus the multiplayer aspect of getting jumped on by a real other player.
Monster, but
The
multiplayer.
Yeah, it's a real person playing as a monster killing you. Wonderful.
So you notice I made one of the curves here red, and I put a dotted line around it. So the A on the dotted line is our area, okay?
Okay.
And then the S around here is our entropy, so counting how many different little nodes fit inside of this area, okay?
Hold on.
And so our entropy is always proportional to our area, or vice versa. So, we could extend this around, and, this would still hold true for if we did the whole circle instead of just a part of it, because the entropy, the amount of nodes will grow with it.
That's what actually.
And so this is starting to get into a bit of Carol's work. And so if area is a measure of geometry, and S or entropy can be related to a measure of energy, or how much energy is in the overall system. Well, if S is proportional, so if area is proportional to entropy, then geometry is proportional to energy. Well, what is geometry proportional to energy? That's just Einstein, right? Because you have your G mu nu is proportional to T mu nu.
Yeah, and the curvature of space-time is equivalent to gravity, and the gravity is equivalent to the energy, positive energy differential. Okay, so that's the equivalence principle in a nutshell.
This is how you find Einstein in Everettian quantum mechanics in a nutshell. This doesn't work for Copenhagen, which is what most people are.
All the little bumps add up to your entropy, and those are all because they're all on a line.
Yeah, so those are all quantum theories of gravity, and this is entropic gravity, which is a little bit different, but it works out better, I think.
Well, I mean, I can see the equivalence. One arc is a bigger arc, and that is your area, and the area contains equivalently all the little tiny arcs.
Yep.
And those could also be seen as branching functions of the
Yes, exactly.
Okay.
So
let's just
pretend we're going to zoom in on
put little forks here on the little bumps, just to make them look like that little trident of the branching function for my own mnemonic purposes.
So we're going to zoom in on this, hypothetically speaking. So let's get rid of all these.
Yeah.
And we'll zoom in on this, and we'll translate this into a more quantum picture. Okay. So our area is going to become our well potential. But different energy states in it. So this is our area. And then we'll have our different well potentials. Of different ways this quantum system could evolve. So these are our different eigenstates. Okay. And we'll notice the same thing. So then each of these will all add up to our entropy S. So again, this is kind of bridging the gap for us a bit here.
It sort of reminds me of how quantum waves come, like different measures and distances and mass. I wonder if that's another fractal.
So, and that's kind of how you can see the quantum wave function in that hyperbolic. So,
yeah.
Well, now we're going to modify this a little bit to reel it back into our space-time coordinate system. Okay, and this is kind of what I've been working on. So let's redraw a graph here. We're going to have start.
Pardon.
See how
All right,
fast I can
those
draw
guys.
this. This will be our T. This will be our M for multiverse right now, but we're going to change it to theta here in a bit. Let's just change it to theta here now. So, obviously we're going to have our X, our Y, and our Z axis in each one of these block universes as time progresses. And each one of these, this would be the universe that each one of these quantum wave functions occupies as the Schrodinger equation evolves. Okay. So again, if we wanted to we can kind of imagine our well potential being around it, and then the waves occupying each one of these smaller. So you should be able to see the overlaps here.
So those different eigenvalues also represent sort of like stages on this pure potential smaller space-time windows on the. Okay.
So we want to
might be jumping too far.
So we can think of so our colored ones are X, Y, and our Z are our spatial axes. So we're gonna say right now this represents a 5D space time, 2 time and 3 space dimensions. We have our 1 time dimension, our regular time dimension going forward through time that we're all familiar with.
Okay.
And then I have written as theta down here. What I normally have written as M, but I'm changing that now. Is our multiversal dimension. How the wave function can spread out into different various branching universes.
Okay.
And so if we wanted to
the number of multiverses potentially increasing with time.
And so we want to figure out, how do we apply a coordinate system here? So if we want to say, so in spatial coordinates, so we're going to be thinking about our time as polar coordinates. We're thinking about our time coordinates as polar coordinates. So normally your polar coordinates is going to be your magnitude. So how long, how far, how forward through time it is, and then theta will be what angle it's pointing at. So you have a distance and you have an angle. And so what we can tell that is so for any point here, let's just say we're going to be at a point here. We got a protractor, and then we'll measure the distance. So we'll say this is like a 45-degree angle. That's in the second time block. Okay, so this tells us which branch of the multiverse we're in. Okay, and then our X, Y, and Z axis will tell us where in that branch we are. So this is sort of like a map through time and a map through space. And we can map this back out to general relativity here in a minute. But the reason that I'm choosing this protractor system for our extra time dimension is because, remember, when we zoom back out into our
ADS.
into our hyper, in our bigger space time.
Hyperbolic space, which could be a anti de Sitter space or just something else. But ADS has a lot of those properties. Yeah.
So we'll say, whatever angle. So we'll have our angles theta, and then our t is our magnitude of the time vector. So, whatever angle on this 360-degree circle we're saying, so say we're going to go on an angle over here, and it goes to the second value, the second energy state in this value. And that'll kind of tell us, which branch of the multiverse we're in. And then we can do our our spatial coordinates from there to figure out where in that piece of time we are, like where in space we are at that time.
Yeah. Gotcha.
And so how do we start relating this back to Einstein's equation? So we can start, figuring out how to modify it for our warp drive. And this is starting to get more on the edge of, this in the fringe stuff.
Right. This is
We
where
want to add another time
this is your
dimension.
unique value added proposition to the field. Yes. Okay.
So, so we're going back to our ds
It
squared.
sounds better than fringe. It sounds
DT.
like, oh, this is where I need to pay attention to. This is where Daniel stands out from the crowd. Right.
So you have our ds squared and dt squared. So our regular time dimension, which in our complex polar time coordinate is the magnitude of our time vector.
Okay.
And again, because it's a time dimension, we're going to do plus here instead of minus. It's, a little squiggly to, so you can see that this is a t and that's a plus easier.
Okay. So it's
And we're going to do theta squared.
squared.
It should be distance theta, my bad. Or d theta.
D theta squared.
Theta squared minus dx dy dz. So minus dx minus dy minus dz. So in our, because of our chosen metric signature, our time dimensions are going to be positive, and our spatial ones are negatives.
So everything it was before, except we added this dimension of multiversality.
Yep, and because it's time, we stick it over here, and then it shoves these over. And so now what this would look like written out in our, so this is going to be the G00 spot still. This is going to become the G11, and then these get all shoved over to the G22, G33, G44. And then, so this would be for 2 dimensions. If we wanted to make it spherical, so a third time dimension. So we're going to add d phi square minus dx minus dy minus dz. And then this one will become our G22, and then our spatial coordinates don't start out into our G33 and our G44 and our G55.
Plus d. So adding d phi squared, that's the number of branches. That's the number of branchings.
The what?
Why are we adding d phi squared to the d theta squared?
So these are our extra time dimensions.
Okay.
So
Those are extra.
theta and
So
phi.
those are 2 different dimensions of time.
Yep. And so it'll tell us where in the angle of our. So remember, it's not just a 2D hyperbolic circle. It's a sphere. So we have to add another. So then these two will tell us. These two will tell us what angle our time vector is at. relative to the sphere, and then the t-axis will tell us how long that time vector is.
Okay. So the phi looked a little bit like the branching function that's used in the wave equation.
No, that would be psi.
Psi. Okay. That's what confused me. It's that camera thing again. I didn't. Yeah. Now it's connected. It was showing right there.
So,
okay.
And where this gets really hard to do is when we extend this out, because remember our big block thing where these are just the rulers, they're not the protractors. So when you add the protractors back in, it bumps the number of PDEs, the partial differential equations, up from 10 equations to 21. So I'm already in our regular 40 general relativity is already complex enough to solve with the one-time dimension. So just by adding in 2 more dimensions, we more than doubled the amount of equations that we have to do.
Sure, that makes sense because, of course, it would increase exponentially.
This is where AI starts to come in handy.
So then my question to our good Dr. Sarfati was along the lines of, do you eventually get to ships and or that behave like beings and where the intelligence is enough where it just innately processes these things as a factor of its own existence, and to the point where you can call it a living ship, or whether it gets sufficiently intelligent enough and sufficiently advanced enough that it can be compared to magic as in Clark Tech, where you get ships that are basically beings, not to go too far out, but that they're organic in a sense, because they either figure this out or perish. Survival of the fittest, I guess.
Mm-hmm.
You make a bunch. You have an AI like your your paperclip generator in that thought experiment, right? Except instead of pumping out paperclips, it's pumping out AI warp drive ships, and they either. So
remember all those modifications that we had to do to just the simple Alcubierre metric just to start to get it to be more physical?
Yeah.
Now imagine having to expand that out for all these extra equations now for multiple time dimensions. You can see where this starts to get like,
you need something orders of magnitude more powerful than ChatGPT. But
you can't do this with ChatGPT.
No, for sure. This is like, but this seems like the convergence of where AI is headed. Like, people wonder what does the AI even look like once it gets to a certain point? I'm thinking, dude, it's doing this. Because eventually it can't be is so smart, it can't be contained on this physical plane of existence, so to speak. And the best we can hope for is maybe to be along for the ride, in the belly of the beast, some might say. Wow, that's interesting.
So are you starting to see how this relates to the multiverse aspect more now after laying it out like this?
Yeah, I can start to see that. I can also see how the number of possibilities of the right answer increases with each dimension you're adding. How the complexity of the calculation increases. But I'm also making important links between the anti-de Sitter space diagram and
there's some cool things I could show you if you want to do a screen share.
Okay, we got 9 minutes, and I think this should be the last round.
Oh, we can do. Yeah, we can do that some other time. Then I can just send you some things later.
Okay. Well, yeah.
That's 4 a.m. here.
God bless you for staying up like this for us. And yeah, I probably have to put some kids to bed. I'd like to think that they find their own way to the landing pad, but I got to land some ships. Yeah, but man, this is coming together for me. I reckon that it's just going to be more sessions and that it's more exciting each time, because it seems like we're covering the same ground, but we're doing it differently. And my understanding is advancing. I feel like, of course, give it another bout of drop of equations and diagrams, and I'll probably feel like I'm skipping a beat again. But it's it's pulling together.
It's
and I
coming together.
appreciate it.
Yeah.
Yeah.
I guess maybe next time we can get into like Pius or his designs or something like that if you want.
Yeah, I'd love to understand. Well, so like we covered how this connects to Dr. Sarapati's work. I would love to see where this connects to Dr. Pais's work. And yeah, anything else you want to mention while we're on this one?
Draw just
I see another diagram.
Quick. So we're gonna have so this is a resonant or piezo superconducting piezoelectric outer wall that's has a magnetic field going through it, and so this is where our magnetic field comes from, and it's also resonating at a certain frequency. In the papers he writes like 100 terahertz, which is interesting. Then inside of here, I'm gonna do a bunch of plasma.
Stem field resonating 100 terahertz. Okay.
So this is going to be our
These are a
plasma.
bunch of
So this is
alternating
our
polarity particles. Plasma. It's your asymmetric plasma. Is that
so
how it
this is
goes?
going to represent our xenon gas. That'll be our plasma. And then here, these are your microwave emitters putting out.
Is there equal number of positive signs to negative signs in that?
No, I just kind of ran.
Okay.
Then he's got microwave emitters pumping electromagnetic radiation
Wonderful.
through the xenon gas. That's how the plasma is made.
Okay. So
And then
you're pumping microwave radiation through xenon gas. Okay. Microwave.
And this here is a dielectric.
The triangle in the middle, I'm guessing that's our ship. It's,
Yep. So this is like where the crew would be,
yeah.
and this is kind of wrapping all the way around.
That's shielded like a motherfucker.
So the inner wall doesn't resonate. It's a dielectric that does not resonate, and that kind of helps act like the Faraday cage to protect the crew. The outer wall is what does resonate, and that's part of the what helps the the waves once they get the macroscopic quantum coherence, as he calls it. That's kind of what helps them, almost like quantum tunnel outside of the ship, and where you can cut. And so, because we have a strong magnetic field here, and then we're pumping strong electromagnetic radiation through it, getting the plasma to drive far from equilibrium, that enables the Gartenstein effect, which is what creates your gravitational waves on the outside of the skin of the ship, or your polarized vacuum, as some people are going to call it. So these are your high frequency gravitational waves. This is your 300 MHZ to 300 GH.
Okay. So by generating this plasma, by hitting xenon gas with high frequency microwaves, xenon activated xenon gas plasma, and then hitting that with terahertz waves. So the smaller bumps are terahertz, and that creates the bigger bumps, which are.
And remember, this is also a superconducting. And then he has it. Then on the inside here, he has your compact fusion reactor that's providing power to the whole thing. So that's what gets this the very high energy densities on this part of the ship. And so then these high frequency gravitational waves, they overlap to make a larger gravitational well that the ship falls into, and that's your warp drive.
Okay. And it kind of, I'll bet that the shape sort of concentrates that toward the front.
And you could, and he even says in his papers that these would be modular arrays laid out in strategic positions on the ship,
right,
and that you could scale it for different sizes and different shapes.
Right. Okay. And that modular concept of that modular premise of your emitters all placed at different locations optimally sounds a lot like that kind of like triangular skin, like the modular skin, almost like nanotechnology that's been described in a few close-up eyewitness testimonies.
Yeah, this thing would be like one big hyper tunable like phased array radar,
Right.
so to speak, on the skin.
Right.
It's to make like a loose analogy.
Right.
And
It's the interesting thing about the fact that we're dealing with time travel and faster than light travel is even if this thing is made in our future, we could have already seen it so many times already.
yeah,
Right.
yeah.
And it does fit pretty closely the description of some of the craft I've heard of.
And so, then we could play with this idea, and then we could start, playing with the shape of it and plug it into the Alcubierre equations and start modifying the shape
Yeah.
and function so it matches this better. And we can kind of see a path forward and kind of
We have
where this
a lot of
where
we have
go.
a diverse array of equations and modules that we can try. And this where Pais gets closer and is maybe that he seems to have hit the rubber to the road in terms of diagramming the actual functioning unit that could mechanically possibly work.
Well, you have to be good to get a lot of his finer points, as he said. I kind of figured quite a few of them out from his podcasts and his patents before I found some of his more in-depth papers that kind of confirmed a lot of my suspicions.
Yeah.
But yeah, no, it's totally a warp
he left
drive.
out that sauce, right? You can't just give that sauce to any old kook. You get a dictator or somebody with this stuff. That's no good. That's no good.
And I mean, like
he's going around. He's modifying the timeline so that all his enemies are killed before they're even born. Right.
Well, this whole concept hinges on having room temperature superconductors. Without room temperature superconductors, this pretty much becomes impossible to build a ship with this because we do have superconductors that aren't room temperature, but then we need to have a cooling system around that, and the amount of weight that goes into like a liquid nitrogen cooling system for a superconductor, like they're doing for like supercomputers, like quantum supercomputers and stuff. It makes the weight and size not viable to put it on a ship unless you're going to do like a fucking big aircraft.
Right. So it's all about lowering that energy requirement, both for the superconductivity and for the warp drive. So we'll call it there. We're at 28 seconds.
All right, perfect.
And awesome, man. Love and peace and warp drives. Talk to you soon.
All right.